When did I put this in? One second. All right, so all right, I want to go over the quiz first. I posted the answer key for you, but let's talk about it anyway. So this was the quiz. Number one, find the critical numbers. So when you're finding the critical numbers, you take the derivative, set it equal to 0. Don't divide out a variable because you lose a 0. So you factor out a 6x, you get x equals 0 over here. And you get x equals plus or minus square root of 5 halves. And if you rationalize the denominator, you can write it like this. So either or. Number two, I said use L'Hopital's rule. So you take the derivative of the top and bottom. So derivative of a to the t is a to the t ln of a. And that's that. And then from there you go to that. And I accept that either answer. I was not happy to see some people write, when they took the derivative, they wrote this. So they took the derivative of a to the t and they wrote 3 ln 2 a to the t. No one writes 3 ln 2. Only computers do that. You just basically, that's the word, framed yourself. So you didn't get any credit for that problem. Then the reason why it's 3 ln 2, in case you're wondering, so it's the people who wrote 3 ln 2, it's because the derivative of a to the t is a to the t ln of 8. Then ln of 8 is 2 to the 3. And then you can bring the 3 downstairs, so it's a to the t times 3 ln 2, and that's the reason why. But the computer just writes 3 ln 2, and you just copied it, and that's how you got it. All right. All right, any questions? No, okay. Let's move along to oh, Brian, no problem. So let's talk about the homework. What was the homework? Oh yeah, the antiderivative section. Questions? (4.19), number 33. Oh, I can see where this threw you off. So remember I said there's no such thing as a quotient rule or product rule when you're taking the antiderivative. And if you get stuck, ask yourself a question of derivative of what gives you that. So I'm going to rewrite this in a different form. 4 times 1 over 1 plus t squared. Does that look kind of familiar now? Derivative of what gave you 1 over 1 plus t squared? The inverse tangent function, right? The inverse tangent of t, the derivative of this is that? Yes? So now I'm in plus c. So now let's deal with the f of 1 equals c. That means if you were to plug in 1 in for t, you should get an output of 0. So the arc tangent of 1, that means tangent of what angle gives you 1? That's the 45-degree angle, so it's pi over 4. So 4 times pi over 4 plus c equals 0. So 4's cancel out. Pi plus c equals 0. C equals negative pi. So the final answer is f of t equals 4 times the arc tangent of t minus pi. Damaris, glad you can join us today. Are you doing better today? No, sorry. I had a student last night in my other class. She's like, sorry, I was not feeling well. I had my second dose of the vaccine, and it was completely sick. All right. So does that make sense, by the way, Mark? Okay. Any other questions? Day, how are you doing over there? Good. All right, let me see here. So 4.9 was 1 through 33 odd. Well, that was 33. Let's do 35. I didn't assign it, but let's see how we do on it. I wonder if next semester we're going to go to the 9th edition of this book. Now, if we do, it's phased in. So when you take Calc 2, you'll still use the 8th edition. They don't just go completely to 9th edition if they do. But the 9th edition of this book has actually been out last semester and this semester, but because of COVID, they decided to keep the same edition. Usually publishers don't do that, but they let Fullerton College do that. So, all right. So go ahead and try to find what f of x is given this. This is number 35. So let's see here. If I take the antiderivative, add 1 to the next one. 2/3 plus 1 is 5/3. Divide by 5/3 is the same as 1 by 3/5 plus c. So the 5 cancel out to what x equals 3x to the 5/3 plus c. If I were to plug in 8, I should get an output of 21. Now 8 to 5/3 is actually not bad. So 8 to the 5/3, that means 8 to the 5th power, then the cube root of it. You could actually take the cube root first, then raise to the 5th power after. This is actually a problem that's designed you can do without a calculator. Cube root of 8 is 2. 2 to the 5th is 32. Plus c equals 21. 3 times 32 is 96. Minus 96 each side. What's 21 minus 96? Negative 75. So, then the final answer is f of x equals 3x to the 5/3 minus 75. Does that make sense? All right, so let's get moving then on the problems here. Since we finished chapter 4, we're going to do 5, 1, and 5 today. So the 5, 1, and 5 today, I get through with. Then on Thursday, we'll do 5, 5, 3, and we should get good as far as our case goes. Then next week is review on Tuesday, exam on Thursday, which is Thursday, April 29th. Then after the exam next week, we got 3 weeks, weeks 14, 15, 16. As completely well observed, a little bit of something.
Yes, thank you for reminding me about that.
You guys hear the big news today? That officer got guilty charge for killing George Floyd. So we will do 5, 1, and 5 together. I have my lecture together with it. So 5, 1 is areas and distances. And then 5.2 is the definite integral. So what I first want to do is go over some basic things that you may or may not have picked up in a previous math class, but it's something you should know going forward. So let's talk about it. So this is the Greek letter sigma. Then write it really nicely. So in math, it means summation. So like, for example, if I were to say this is sigma, and then there's I equals 1 to, let's say, and I put a 5 on top. And then this is the expression, and then I'll explain what it means. So if you see something like this means sum up all the terms from I equals 1 to 5. Why 1 to 5? Because this is your starting point, and this is your stopping point. So 1 is the starting point, 5, where 5 is that's the sign. So that means you're going to plug in 1 for I. So if I were to plug in 1 for I, what do I get? 2 times 1 plus 1, right? That's my first term. plus, what's the second one? Well, we plug in 2 for I. So 2 times 2 plus 1. Plug in 3 for I. Plug in 4 for I. And then plug in 5 for I. Now how do I, then you stop. Why do we stop? Because the 5 is up there in that I highlighted in orange. That's the number that you stop at. So this becomes 2 times 1 is 2 plus 1 is 3. So 3 plus 5 plus 7 plus 9 plus 11. Then you add them up, 35. So the summation is 35. Does that make sense? Okay, so let's say I ask you to sum, and it doesn't necessarily have to start from I equals 1. Let's say they could say I equals 3 to, let's say I equals 6 of I squared. How would you do this? That means 3 squared plus 4 squared plus 5 squared plus 6 squared. Why did I stop at 6? Because that's the number that's up here. Why did I start at 3? Because that's the number that's there. So then you just do the calculation. That's 9 plus 16 plus 25 plus 36. So the answer is 86. So sigma notation is supposed to make things easier to write. So let's say if I were to say summation from I equals 1 to 100 of I, that means add up all the numbers from 1 to 100. So this would mean 1 plus 2 plus 3 plus 4 plus ... plus 99 plus 100. Instead of me writing all 100 numbers out, in math, we just write it like this, and it tells us, hey, that's what I mean. I mean add up the numbers 1 through 100, but I wrote it in very small terms. So this sigma notation is supposed to help us write things a lot easier, as opposed to writing 100 numbers out. Kind of like scientific notation in chemistry class, you know, you would write 2 times 10 to the 17th power, or minus 17th power, instead of you writing 0.0000, bunch of zeros before you write 2, well, you can just write 2 times minus 17, minus 10, 2 times 10 to the minus 17. I just need that number up. That's, so that's what sigma notation does. All right. So, by the way, what is the sum of the numbers 1 through 100? We'll do that in a second. So let me give you a formula now. The summation of the numbers I equals 1 to n of I. Now, what is n? N is some number out there. 100, 200, 300, it's some number. The summation here would be n times n plus 1 over 2. That's a nice little nifty formula. I used to prove this by mathematical induction for my calculus classes, but I think it turned out not to be a good idea because people freak out. So I can do it for you after class if you want. How many of you have seen proof by induction? So it wasn't so bad for me because I learned it. I learned this little induction stuff in high school, but apparently they don't teach it in high school these days. You just sit in a circle and talk to each other in high school. So, all right, fine. No humor in this class. Only a couple of you got that joke. The rest of you were offended. I got to be careful what I say these days. I was watching the news. This person came on, I don't know what channel it was, and there was this hardcore liberal. Hey, math is racist. 2 plus 2 is 4. Why? Why does it have to be 4? I'm like, what are you talking about? Math is racist. Math is like the least racist subject. It's like you can know any language and do math. Yeah. Moving on. So what was I doing? Oh yeah. So if I wanted to, I'm going to give you the formula. So summation from I equals 1 to 100 of I, you can actually use this formula. It would be equal to, so in this case, your n is 100. So 100 times 100 plus 1, which would be 101. Let me just write it as 101 over 2. So then you just take out your calculator. So that would be 5,050. And that's it. Now, does this make sense so far? So that's a nice little formula. I just literally added the numbers 1 plus 2 plus 3 plus ... plus 99 plus 100, which is 5,050. The other way you could do this is take your calculator out and literally go 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8 plus, all the way to 9,900, and you will eventually get 5,050. Unless you mess up somewhere and you press the wrong button and you add 57 twice, then you're going to mess it up. But this is a nice little formula that you could add up all the numbers. Now, I'll tell you an interesting story that has nothing to do with what you need to know for the test. So there's famous German mathematician Gauss, and when he was in elementary school, whatever, 4th or 5th grade, he got in trouble. And remember, this is like hundreds of years ago, so there was no couple hundred years ago at least. Wait, when did Gauss leave? Okay, anyway, it was before the age of calculators. And he was in 4th grade or 5th grade, and he got in trouble. So his teacher said, I want you to go into the corner of the room, don't come back until you add up the numbers 1 through 100. This is a true story. So Gauss went in the corner of the room. Less than a minute later, he came back. He goes, here you go, to the teacher. And the teacher was shocked. They're like, well, wait, this is really, you think the answer? He goes, yeah. So here's how he did it. He said, all right, you want me to add the numbers 1 through 100. 1 plus 2 plus 3 plus ... plus 49 plus 50 plus 51, 52, ... 100. So let's add up the columns. 1 and 100, that's 101. 101, 101. So how many 101s do I got here? 50 of them, right? So it's 50 times 101. And then you go, well, that's just, and then you go ahead and multiply 50 times 101 and you get 50, 50. That's pretty cool, huh? Now, it's not that impressive when I do it, but if someone who's in 4th grade comes up with that, and I didn't come up with it, I learned it from my teacher, but Gauss, being in 4th or 5th grade, he just came up with it himself. He was a genius. He's like one of the greatest mathematicians of all time. In fact, in Germany, Madison, you'll appreciate this. It has to do with Germany. Before they went to the euro, he was on the Deutschmark, like of one of the bills. They had his picture. That's impressive. A mathematician getting on money. That's money. Okay, that was a bad joke. Then they made this mistake of going to the euro, and they have to deal with all the other European countries. That drags them down. All right. Although Switzerland never made that mistake, they stayed out of it. They're all like, we want nothing to do with other European countries. We're neutral. Moving on. So here's the bottom line. This is what you want to remember. And this is in your book. You don't have to memorize this. In fact, I don't even make my students memorize this back in the in-person exam days. If you have the summation from I equals 1 to n of I, that's n times n plus 1 over 2. Similarly, if you have the summation from I equals 1 to n of I squared, the formula for that is n times n plus 1 times 2n plus 1 over 6. Now, why the heck? So if you were adding up the first from 1 through any number, the sum of their squares, you can use this formula right here. So these come in handy for later, this guy and this guy. Now, more on that later. All right. Now, here's what we're going to do. And this is in your book, by the way. If you go to page, let's see here. I think that's actually in the 5.2. Oh, I don't know where it's at. Moving on.
Professor, that's a number 6, right? On the second one?
Yeah, that's the number. This on the denominator, yeah, it's a 6, yeah.
Mm-hmm.
Oh, I can't even draw a y-axis. So let's look at the function y equals x squared. Okay, so 0, 0, 1, 1, 2, 4. Well, look at that problem. Wow. This is f of x equals x squared. Now, here's what we're going to do. So what if I said from the interval 0 to 3, I want you to find the area underneath the curve? Okay, no problem, Maris. So I was going to ask Damaris, do you guys have a Discord for this class where you can you share notes with each other? No. Yes. Okay. Yeah, because there's an emergency. One of my students have to. Okay. So imagine if I asked you to find the area. This is a little hard to explain with an iPad. I've never done it before. Okay. We want to know what's the area underneath this curve, f of x equals x squared, going down to the x-axis. So notice it's not a nice shape. It's not like exactly a triangle or a square or circle where I know a formula from geometry. It looks like a triangle, but it's really not a triangle because it's a curve. So how would I get this area underneath this curve? So what we're going to do is there are a few things you can do. Give me a second here. So what we could do is approximate the sum by making rectangles. So for example, let's say I'm going to divide this x-axis into 3 regions. I'm going to create these rectangles, these red rectangles. And notice these red rectangles that I'm creating, they're a little too big, meaning I'm not going to get, there's going to be an error in my area because the area of the rectangles added together is actually larger than the area underneath the curve. But again, this is an approximation. So this is a situation where I'm letting n equal 3, n being the number of partitions that I broke up this interval from 0 to 3 at. And now to approximate and getting the upper sum, so in this case, the upper sum would be R3. So R3 is the upper sum in this case, because when I take the point from the right side, I'm getting an approximation that's on the high side. So this is an upper sum. Now, how do I get the area of underneath the curve? Well, what I'm going to do is approximate getting the areas of these rectangles. So what's the area of this first rectangle? 1 times 1, right? Because it's width times length. Plus, what's the area of the second rectangle? It's 1 times 4. What's the area of this third rectangle? 1 times 9. And if you add them all up, you get 14. So the area, I should put this all in red. R3, that's the upper sum in this case, is 14. Now that's not the exact area, that's the area using the right-hand side. That's the upper sum. Now in this case, the lower sum is the same as if I were to get the sum from the left side, so L3, meaning they're using the left endpoint. So what I usually do is just, let me erase the, okay. So now what I'll do is I'll use a different color, and the lower sum would be I would get the left side, meaning for each little partition, I'm going to get the left function value as the, I'm going to use that, and in this case, it's just going to be a 0 on this side. So what I did here is, let's look at the interval between 2 and 3. The reason why between this interval, between 2 and 3 right here, you see where my cursor is at? I'm taking the left part of the rectangle, which is at x equals 2, and I'm getting the function value there. So that's where the height is. So between 1 and 2, I'm using the left side. So the function value is 1. Here, between 0 and 1, the lowest function value, or the left side's function value, is 0. So the height would be 0. So there's really no rectangle in this case. Now, to get the L3, that would be 1 times 0, because the height is 0. The second rectangle would be 1 times 1, and the third rectangle would be 1 times 4. So that's L3 here that we're talking about. And that would be 0 plus 1 plus 4, which is 5. So the lower sum is 5. The upper sum is 14. The sum of the rectangles, that is. Now, the actual area between underneath the curve, which is the curve right here, the actual area underneath this curve is really somewhere, the real number is between 5 and 14. Now, how do I get a better approximation? Because between 5 and 14 it's not a good approximation. That's a wide range. And it's not necessarily halfway between the two. Well, since we used n equals 3, what if I made n equals 6 and I divided up these rectangles into even further pieces? Do you see how my error would be less if I used more rectangles? Let me explain. Now, I'm not going to do it. Just go to this page here. Let me just make this a little bit wider here. So let's just say you had some curve that looks like this. So notice, if you're trying to get a decimal approximation, there's an error here. But if I made more rectangles, the error amount would get smaller. Because then you can just erase this little part right here, erase this little part here, erase this little part here. And then what if I made n even larger? Then the error would get smaller and smaller. So what I'm trying to say is, well, what if you took the limit as n goes to infinity? Wouldn't the error go to 0? So if I kept creating more and more rectangles here, so what would happen is here, these would go away, and the error amount would get smaller and smaller and smaller. See, the amount of error is very little now. So if you take the limit as n goes to infinity, the error would go to 0 and you get the actual area. So that's what we're trying to do here. And what we're doing here is called Riemann sums. It's not pronounced Riemann, it's Riemann. I think that's a German name as well for Madison. So, and also notice as these rectangles get smaller and smaller and smaller, the left endpoint and the right endpoint get closer and closer to each other for each of those little rectangles, right? Since as rectangles keep getting smaller and smaller and smaller, the left endpoint and the right endpoint almost become the same point. So does it really matter when we have a rectangle that I'm representing here? Does it really matter which x value that I pick, the left side or the right side or somewhere in the middle? No, because as you make n larger and larger, this rectangle is going to get super thin. And it gets thinner and thinner and thinner. So it really doesn't matter what value you pick in there because they're almost going to be right next to each other anyway. How close are they going to be to each other? As close as you want it to, because as n goes to infinity, that rectangle is going to be paper thin. Does that kind of make sense? I know this is especially tough for me to teach on an iPad. So I'm doing my best here. Now, when I get through the couple of examples, I'll tell you exactly what you need to be able to do on a test. So relax. So let's talk about the area here. So the area underneath the curve is going to be the area of could be approximated by adding up every single one of these rectangles. So the area of the first rectangle will be f of x sub 1 with a little star. Don't worry about the star, just put it and I'll explain it, times delta x. So when I'm getting the area of the rectangle, the delta x is the width of the rectangle. The height of the rectangle is the function value, which is f of x. Now, what f of what though? F of 2, f of 3? Well, it's x sub 1, that first rectangle that you see. So what I mean by that is this. If you're dividing it, if you're getting the area underneath this curve and you're getting these rectangles here, so let's say this is x sub 0, x sub 1, x sub 2, x sub 3. X sub 1, actually, I should say, this is A. Let's say we're going from A to B. So this would be x sub 0, x sub 1, x sub 2, ... x sub n. F of x sub 1 star would be the first interval, any x value in that interval. That's the star means any value, because this is going to get thinner and thinner and thinner. So it's just the arbitrary, it's just a general x value in that interval. So this part right here will give me the area of this rectangle, plus f of x sub 2 star times delta x. That will give me the area of the second rectangle. Now, I'm not saying there's only 3 rectangles. This is just an arbitrary, this is just the general picture. There's n rectangles here. Plus, keep in mind, I know this is very tough and half of this is flying over your head. That's perfectly understandable. And then it keeps on going, plus ... plus f of x sub n star times delta x. Till the last rectangle. So I'm dividing it up into n rectangles. Let me draw a better picture. So this would be the area of the first rectangle. This would be the area of the second rectangle. Third rectangle, plus ... Let's go with purple. And then the last rectangle would be this one. And then this distance from here to here would be delta x. How many of you are kind of with me here? How many of you are lost? Now, when I say how many of you are kind of with me, I'm not implying I'm going to expect you to do this on a test. I'm just saying, because it kind of. So this is approximating the area of an approximation of area underneath the curve. And the way we're approximating the area underneath the curve is we're drawing a bunch of rectangles, and we're going to add up the areas of every single one of these rectangles. And then when you add up all the areas of those rectangles, you get an approximation of area underneath the curve. It's not exact because there's going to be some error here, as you can see. And every single one of these areas, I color-coded it. So the area of this first rectangle is f of x sub 1 star times delta x. Because what's the formula for area of a rectangle? Width times length. So delta x is your width. The height is f of x. Now, why did I call it f of x sub 1 star? The x sub 1 star is just some x value in the first interval. Don't let the star throw you off. This author likes to use the star, so I use it. You can just say f of x sub 1. So any x value you pick in here and you take the height of it. Now, does it really matter which height you pick? No, because eventually they're all going to give you a different approximation, but they'll be close. Then the second one, this is some x sub 2 value star. So let's say your x sub 2 star is here. Your some x sub 3 star is right here. So f of x sub 1 star would be the height of it. So the height times the width, and that gives you the area of the orange. The second rectangle, that's the area of the red. The third one is the blue, and then the last one is the purple. So that's an approximation. Now, why did I put an approximation sign, the wave equal sign? Because there's an error there. All right. Now, if I were to, the exact area is equal to the limit as n goes to infinity of what I just wrote. F of x sub 1 star times delta x plus f of x sub 2 star times delta x plus dot, 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 all the way to the last term, f of x sub n star times delta x. So it's the same thing as I wrote up there, but limit as n goes to infinity, then gives you the exact area. Now I could actually write this with summation using area equals limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I star times delta x. So that's the limit. We're taking the limit of the Riemann sum. All right. I realize I'm not doing my best work because this is a tough section to teach as it is, and I'm using teaching it on the iPad for the first time. It's not doing well. Ali, are you still here, or she's gone? All right.
Sorry, Professor. I'm just double checking on the area, the second one, the second area. Is that a star? Is that x1 or yeah?
Right.
Right where it says function parentheses.
This
X,
one right here.
Oh, it's I. Okay, thank you. Sorry.
Yeah. So you're doing the summation. So as you're plugging in, you plug in I equals 1 first, you get this term. Then you plug in I equals 2, you get that term. You plug in I equals 3, then you get the next term. Then you go all the way to n, which is the last term, and then you stop. This is just the sigma notation of that. Oops.
So everything in that blue box is the limit of Riemann sums, of the Riemann sums?
Yeah, limit of the Riemann sums, yeah. Basically, the Riemann sum is when you're adding up all those little rectangles, it gives you an approximation of underneath the curve. But if you take the limit as n goes to infinity and those rectangles keep getting smaller and smaller and smaller, then you're going to get the exact area. So let me go over a few things here. Let me give you the definition of the definite integral. The definition of the integral that is, if you want to find the area underneath the curve from A to B, all the way down to the x-axis, can be denoted as, this is the integral symbol. It's like a stretched out S. And you put a little a underneath and a b above it of f of x dx. That is equal to the limit of the Riemann sums, which is the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. Now, this next part is a little tough to explain. What is delta x? Well, delta x will be equal to b minus a over n. Here's why. If you have a curve and you're partitioning it from A to B, you're partitioning it to, let's say, n rectangles. Let's say you're partitioning it into, let me make it better. Let's say this is A, and let's say this is B. Let's say you're partitioning it into 1, 2, 3, 4, 5, 6 rectangles like I just did here from A to B. So this would be, so in this case, if this is 1, 2, 3, 4, 5, 6, 7, what would delta x be? Delta x would be 7 minus 1 over n, and which is 6 here. So it would be 6 over 6, which would be 1. And that gives you delta x, which is the width of the rectangle. So the width of the rectangle is delta x, and the formula to get the width is b minus a over n, which is the distance over the whole interval, which is 6, divided by what you want n to be. And I wanted n to be 6, meaning I want to partition it into 6 rectangles, so it would be n equals 6, so it would be 6 over 6, which is 1. Whereas, let's say somebody else doing this, they wanted to partition it into only n equals 3. So if you wanted n equal 3, so you get delta x to be 7 minus 1 over 3, which would be 6 over 3. That would mean your delta x is 2. Why? Because look at the rectangles now. The width of the rectangles is 2. So far I have gave you this formula, which is important. It's saying a definite integral is the limit of the Riemann sums, and delta x is equal to b minus a. Also, x sub I is another value that you need to know, other thing you need to know. What is x sub I? I promise you this is the last thing. X sub I is going to be a plus I times delta x. Oh, Ryan, yeah, we'll do examples with numbers. So, oh no, Aaliyah, it's too late. I was going to ask you if the explanation made sense, but
Oh, my bad. I'm sorry. I just had to walk away for a little bit.
oh, it's okay. I'm having a heck of a time. This is my first time explaining Riemann sums on iPad. Oh. So I'm not expecting you to fully understand this, finishing this class. You just pick up what you can, okay? And I'll tell you the part that I expect you to know. Once we start doing some problems with numbers, I'll expect you to tell you, hey, you need to know this for the test. So what is the A plus I delta X means? So your X sub i's, when you're picking your rectangles, let's go back to more rectangles here. A is your starting point. So each time you want to pick an X sub I, an X value, you start from A, and then you move over delta X. So when I equals 1, let's say it's this. I equals 2, it's this. I equals 3. And each time you're moving over to the next partition and picking out X value. So you use that as the height. So that your X sub I is basically, you're moving over I times delta X. How much do you move over? Well, it depends on what delta X is. Sometimes delta X is going to be a larger number. Sometimes it's a smaller number, depending on how much you partition it. So this is you moving over. We'll do this is what X sub I is. So let me pick a better example here. So let's say you're starting at A equals 2. So A would be 2 plus I times delta X. Let's say delta X was 1. So you start at 2, then when I equals 1, then you're at 3, then I equals 2, you're at 4, and so on. You're moving over each time so you can get the height at that rectangle each time. So you're adding up the area of the boxes. Let's just do an example, and I'll tell you exactly what you need to know. This is probably one of my worst jobs of explaining. I understand that already. All right, let's go back to the part. Okay, after saying all this, just write down the highlighted areas right here and put a star next to it. Just make sure you write down those highlighted areas and copy everything down from everything that's in this box right here. Just copy down this orange box. Okay, we're going to start off easy. So right now, what I'm going to do for the next couple of questions, this is a definite integral right here. We're going to write a definite integral as the limit of a Riemann sum. And you should be able to write a limit of a Riemann sum as a definite integral. We go back and forth. We'll do the easier one first. If you write a limit of a Riemann sum as a definite integral. So let's just do some examples. Unlike your physics professor, when I do a bad explanation, I know that you didn't understand anything I said. Whereas the physics professor thinks everything is hunky-dory. Let's move on. Let's do some triple integrals. Oh, I know you guys want to take a break soon. Let me just do a couple examples before we take a break. All right, so what I wrote in black is the question. What I do in red will be the answer. Express the limit as a definite integral. So limit as n goes to infinity of the summation from I equals 1 to n of x sub I squared, get the star is not there, that's fine, times delta x on the interval 0 to 5. How do you write that as a definite interval? Now you have this stuff that you highlighted, you follow that. So the answer is, are you ready? Don't blink, otherwise you're gonna miss it. Are you ready? Here's how you do it. It's the integral from 0 to 5 of x squared dx. And that's it. That's how you write it as a definite interval. How did I get that? Well, 0 to 5, it's right here. Your x sub I squared just becomes x squared, and the delta x becomes dx. And that's how you write it as a definite interval. Now, I know you're wondering what the hell is going on. Where's the big picture? Don't worry about that. Just figure out how to do this right now. We'll get to the big picture later. Did that make sense? Did you understand? Can you do that? All right, let's do another one. Baby steps. We're just doing these right now. Do your best to do this next one. All right, do this one. Do the best you can. I'll do it in a minute. All right, so you should hopefully be done by now. So the answer is, so the answer will be the integral from pi to 2 pi. When you write it in as a definite integral, the smaller number is always on the bottom, the larger on top, just like the smaller number is on the left, larger is on top here, on the right. Of cosine of x over x times dx. How many of you got that? All right, let's do one more for good measure. Limit as n goes to infinity of the summation from I equals 1 to n x sub I star. Except sometimes it has a star, sometimes it doesn't. It doesn't make a difference. All right, do that one. All right, you should take long to write it down. And so the answer is going to be the integral from 1 to 3 of x over x squared plus 4 dx. Did you guys get that? Yes, okay. All right, so let you guys take a break. We'll start back at 4:30 to do one more example. Going backwards, we're doing a little more work on it. We'll start at 4:32.